Hello everyone. Let us discuss about very important concept called singular value decomposition. This is a very extremely important concept. It's used in many of the algorithms. So let us discuss this concept. So uh, okay. So you can find this notebook in links provided in the description. So let us discuss. So let us assume that we have this particular matrix 3 2 2 2 3 1. So it has 2 rows and 3 columns array. So we have to decompose it. So we have to decompose it into this particular format. This is called svd format. Wait. Yeah, so you want to decompose this particular matrix into this particular form. The reason why is it has very advantages, many advantages with this. So it's very easy to with respect to the rank. If you want to identify what is the probability that or likelihood of availability of a particular feature or particular sample space, it's this particular svd decomposition is very helpful, and this is helpful in many different ways. So given a matrix, what you do is we'll factorize into 3 different matrices. So then you multiply these 3 matrices, again you get back this particular a matrix. So it looks very simple, but decomposition is difficult because we have to apply algorithms and everything. So let us have an array. Okay, this is a particular set of an array. The concept here is, first what we do is we will multiply a with a transpose. So what is a with a transpose? So let us print a. Okay, so indentation is not good. Okay. So this is a. Now if a transpose is interchange of rows with columns. So when I interchange the rows with columns, you can see this rows becomes into this columns. So what we are trying to do is we are going to multiply a with a transpose. Why we are going to do it is to find out eigenvectors and eigenvalues. So in my previous topic, I mentioned about a very simplified version of eigenvalues and eigenvectors. I have to cover more. So I will give one of the deep dive demos, how to exactly we have to do this eigenvalues and eigenvectors. Still a part of eigenvalue and eigenvectors decomposition have done with respect to this paper which is shared here. So this example I have taken one of the paper. The description is also, you can find it in the description, the link for this particular pdf. So what we are doing is, first we are going to multiply a with a transpose and we'll get this particular matrix. And this matrix, what we find is we try to identify singular values. So singular values are nothing but the roots of this one for eigenvalues. So this is something I can explain in some other videos. So for now, just take for granted that given this is an algorithm. So you get a matrix, you multiply with a transpose matrix, and then you find out a determinant with the help of lambda, and then from lambda you will find out the roots of this particular equation. So roots we will find out by 25 by 25. Now let's see how we do it. So here I have a matrix. Okay, so I have multiplied with this matrix. You can see I have multiplied this matrix, and I am able to, and I am using this simple numpy library eigen. So where I am printing out eigenvalues and eigenvectors. So once I get this eigenvalues and eigenvectors, I use it in next subsequent levels furthermore. Okay, so that is our first step. Now once the first step is over, what we do is we'll take the root. So this is the first root here. So our first root is 5, and we'll square that root 25, and then we separate a transpose with 25 identity matrix. So what is identity matrix? So let me show the identity matrix here. So if you see the identity matrix, you can see this is nothing but the diagonal matrix with filled with number 1. So what we are doing is we are taking one of the roots, multiply with identity matrix, and separating with a transpose a. Now here you have to maintain a caution. Earlier what we did is we have done a transpose a. Okay, now what we are doing is we are doing multiplying with a transpose with a. See, earlier we have did a with a transpose, now we are doing a with a transpose. and we are getting this particular matrix. After we getting the matrix, we are subtracting with one of the roots with the identity matrix. So then we'll come up with this particular matrix. Now after coming with this particular matrix, what we have to do is we have to get the reduced form. So again, this is one of the matrix concepts. So matrix concept is when you get a particular matrix like this, you have to reduce it into final form. So we have something called row operation and column operation that you can check it out in echelon form for matrix. You can make a Google search and find out about it. So what we are doing is we are doing row reducing. Means, for example, if we see this particular first row, if we subtract the first row with the second row, we get the list of zeros, row of zeros. So row of zeros, we put it in the row number 3 and make it more like a diagonal matrix. So when we reduce this matrix, we try to find out the unit vectors. So why we are all doing this? We are doing this in order to find the decomposition, that SVD format which I have showed in the front, like this one. So in order to get this matrix, so we have to follow these particular steps. So these steps normally for machine algorithms we don't have to do, because we already have libraries for that. For only this is just to explain how we get this decomposition of a matrix. So first what we do is we have multiplied with A transpose. We got this eigenvalues and this, especially with these roots. So again, when we did A transpose A multiplied with A transpose A, subtracted with the roots from the first equation, and then once we subtracted it, we get this particular matrix after subtracting with the root of the identity matrix. And then we got a particular matrix like this after reducing to a lower form. So we use something called SPy. So NumPy, these libraries we have used NumPy. We are used something called SPy. So SPy is something SymPy. So SymPy is something, it's also an open source library. You can use this. So here I use this library in order to reduce it from this matrix to this particular matrix. I will share the link for matrix reducer so that you will understand more. Now here what we are doing here. So there is a problem with this particular library to convert into normal matrix like this. So so for that we have to do this certain process. So what we are doing is we are considering this first matrix as some kind of a string array, and then string array we are converting into float array so that we can make it a normal NumPy array. This is very important step, otherwise we are getting garbage values. Okay, another way of reducing is using a method. This is one Python method which I have found it in the internet. So this is another way where you can reduce the matrix from this level of matrix to this level of matrix. Either you can use this library function, or you can do it on your own with the help of this Python function. So here what we are trying to do here is we are trying to make a unit vector of the first row. So first row means, so this is the reduced matrix you get, and then what we are doing is we are trying to get the unit vector. So unit vector, again we have a particular algorithm. So when we have this method, you will get the unit vector. For example, if you have this array, so when you have this array, what you can do is you can wait, let me copy paste here. So when you have this array, so when you try to get the unit vector, so what will happen is it will calculate the distance. So that means it's the square root of 3 square plus 6 square 4 square, and divide each element with that respective value, and finally you end up like this. So similarly, so given this matrix for the first row, so what I'm doing is I'm trying to get the unit matrix. So this is the unit matrix which I get. So this is the third step that we have to do in order to get the decompositions. So similarly, earlier, if you remember, we have two roots. One is 25 root, another is 9 root. So we have followed this process by subtracting this first root, that is 25, with identity matrix. Now we have to do the same thing for the second root with the 9 matrix. So once we get the matrix, we'll reduce the matrix into this particular matrix. After reducing the matrix, we convert it into a normal array. After converting to normal array, we'll take a first row, and then we are getting the first matrix. So actually there is a pretty confusion how this process is happen, how the 3 by 3 matrix is converted into unit matrix. So this is one way. I'm assuming that this is how internally the eigenvalues decomposition are done. But if you see in this particular lecture given here, they say that so this is for the second time, this is for the first root, this is for the second root. So this is the unit matrix you are supposed to get, but I am getting 0 over here. This one I am getting on the top, and this one I am getting 0. So probably I might have done some mistakes, so I just leave it there for your reference. Know how we calculate the vectors for the matrix. I just given you some examples so that you can work more on it. Okay, after finding first two vectors, so you have to identify the third vectors, because this is the 3 by 3 matrix. So the third vector, what we are doing is so v1 v2 they are perpendicular. So when v1 and v2 are perpendicular, and if there is a vector exists, we don't know, like vector is we don't know, so we have this a b c as a vector. So what we are doing is we are finding out the two equations. One equation we get a minus b, and the second equation we get this one, a equal to 2c. So how we are doing it? By using this with the help of this function v2 3 equal to 0. So we get this particular function. So we get v2 as like this, and if we consider the unit vector, then this third vector will convert it into like this. So once you have these three vectors, so we have actually formed the final matrix like this. So this particular matrix, so this is the first matrix, this is the second matrix, and this is the third matrix. So here what I did is I have hard coded the values here. So in order to explain, like if you multiply these three matrices, we'll again come back to this first matrix. So and then this one, the middle one, diagonal one, if you see, these are the roots. So 25, square root of 25 is 5, and square root of 9 is 3. So 5 and 3. Since our matrix is 2 by 3, so we have diagonal matrix like this, 5, 5, 3. And these are the two. I will show you how to get this the first matrix. So that is upper matrix we call. So for upper matrix, there is a procedure we have done. So yeah, this is one. So remember when we did a transpose A, we got this eigenvalues. These eigenvalues are the roots. Now eigenvectors will be the first matrix. This is nothing but 1 by square root minus 1 by square root, 1 by square root of 2, 1 by square root of 2. So first eigenvector that we got it from the first root will be this one. So let's see what will happen if we multiply these three vectors. So these three vectors I have here. So what I am doing is I am multiplying the first vector with the second vector, and this is the result. I am multiplying with the last vector. So let's see how it comes. So you get almost similar values. 3 1 2 1. This is 2 3 2. So almost the similar value that we did this one 3 2 2 2 3 minus 2. So this is how we will have this svd decomposition. So actually for normal machine learning algorithms, you don't have to do this particular step. So what you can do is you can directly use this particular library. From this library you can invoke this svd and call this particular a matrix. When you call this matrix, it will automatically give you those values. Only one catch is you will get the second vector something like this. So what you have to do is you have to make this in order to verify whether these three are multiplying these three, whether we get the first matrix. What we have to do is we have to make it as a diagonal vector, and this is this 2 by 3 matrix. So the last two matrix we have to make it 0 0. So once we do that and we multiply back, see here we are getting the same matrix. So this SUVD decomposition has a lot of importance. So it's a very good concept to learn. It is used in PCA algorithm, LDN algorithms, and lot many algorithms, even for the rank matrix and classifications also. So this is one way of mastering this particular SVD algorithm. So thank you. Yeah, bye.